Okay, and now it's another day. I think you are all on the edge of your seats trying to find out about the inner products which exist on the Fourier space, which I was commenting were like the only reason why we use the Fourier space, or I guess maybe the primary reason. There are other reasons why we use it, but the primary reason, like one of the great reasons why we use the Fourier space. So many great reasons why we use the Fourier space. This is one of them. So let's talk about how we can guarantee that there's an inner product on the Fourier space first. And so this first thing that I'm going to cover has a name. It's called the Cauchy-Schwarz inequality. And it's just the defined inequality that if I take the inner product of two vectors and then I consider their magnitude, recall the inner product will be in the complex numbers, so then I could take the magnitude, the complex magnitude of those, and that's always going to be less than or equal to the magnitude of each of the vectors separately. So on one hand, I'm taking an inner product, I'm extracting a complex number and then taking the magnitude of that. And then on the other hand, I'm actually computing magnitudes of vectors. And there's this inequality that is always true. This is actually always true for any inner product space. So long as you can perform an inner product on two vectors, you will always have this property. This is the example of the property in R3. And so I've provided a proof of that property in R3 just so that we can see how it's done. And the way we do that in R3 is that we expand. So we're going to compute the dot product of two vectors in R3, and that's what's in our parentheses there. We square it because it'll necessarily give us the magnitude squared if we square that, because we're in the real numbers, not the complex numbers. And that's going to give us each of the elements squared, but it's going to give us some of these extra terms which I've written in red, green, and blue, right? And those are just coming from foiling. In R4 we'll have 4 extra terms and so on. So we have those 3 extra terms from foiling, and we can also compute the squares of the magnitudes of each of the vectors separately and multiply them together. And if we compute those separately and multiply them together, we notice that there is an equivalence between these terms in black of each of the two of them, but the terms in red, in green, and blue differ just a little bit. And so if we just look at one of the terms, they're all basically equivalent to one another. So if we just look at one of the terms, I'm claiming that the bottom term is larger than the top term. And we'll see why that's the case right here. So if I scroll down, it's not too difficult to see that if I were to take the bottom term and subtract the top term, so this is the bottom term minus the top term, I can rearrange that quantity as another quantity squared. But any quantity squared, no matter what real number I take, because this is definitely a real number, if I square it, it has to be greater than or equal to 0. Okay, so if that makes the bottom term minus the top term greater than or equal to 0, that means that the bottom term has to be at least the same size as the top term, which is what this line is saying. And therefore, we come to the conclusion that this collection of magnitudes is greater than that one. There you go. So that's how the proof works, and we can extend this proof to any number of dimensions. I'm going to scroll down really quick and then I'll jump back up there. So we can extend this proof to any number of dimensions, and in fact I'm claiming that this is true for C infinity. Now for it to be true in C infinity, every single term in the inequality must actually exist. So really what I'm saying is that this is true in C infinity, I should say, so long as this, that, and that are finite, right? We want to make sure that we're dealing with finite things. Otherwise, you'd like to be a freshman who says infinity is less than or equal to infinity, which has somewhat of a meaningless sense to it. So we want to make sure all 3 of these terms are finite, but so long as they are finite, and actually, in fact, so long as the 2 terms on the right are finite, because we'll see that the proof includes that these 2 being finite will force the one on the left to be finite. So long as the 2 on the right are finite, then we actually gain Cauchy-Schwarz in C infinity as well. Now this doesn't look like, a lot of you might be saying, why does this look like a dot product or an inner product? And why do these look like magnitudes? Well, if we think about it for just a few moments and we jump up back to where we were before, right up here, if I look at the inner product of two vectors, that can be represented as a sum of A's and B's, right? So it's the sum of A's and B's. I could represent this with sigma notation if I wanted to. Meanwhile, each of the magnitudes, I could represent them individually with sigma notation as well. So just representing an infinitely long vector with sigma notation, this is the way we could represent the inner product of two vectors, and these are the ways we could represent their magnitudes. Okay, so we can prove this in infinitely many dimensions, basically just by proving it in finite dimension for each capital N. We can do the exact same process we did before, no matter how big N is, and then the inequality is preserved under limits, right? So some sort of, as long as it's a less than or equals to inequality, if it were strictly less than, that wouldn't be preserved in limits, but an equals to inequality is preserved under limits, so we let capital N go to infinity, and we see that that's true under limits. Let's jump back up to the example now. So here's an example of maybe Cauchy-Schwarz working in R3 for us. If we just take a nice collection of two vectors in R3, we can compute their inner product and its magnitude, and we get 2. We compute one of their magnitudes independently, we get root 6. We compute another one independently, and we get root 3. If we look at what's the value of 2 compared to root 6 times root 3, which is about 4.24, we do see that the Cauchy-Schwarz inequality works. But let's move down to maybe one of these infinite dimensional cases. Really, what this is now in the infinite dimensional case is this is a statement about series and sequences. A statement about series sequences, right? So if I'm summing sequences is the idea, or I can make the statement about series. And so if we grab an example of one of these, here's a nice example of Cauchy-Schwarz in what I would call infinite dimensions, even though it's really just saying what is this nice inequality which relates to series and sequences. I can take this sequence, n squared minus 1 over n to the 4th, and I can sum that entire sequence from n equals 1 to infinity. And if I break that sum up and pretend like it arose from an inner product of two sequences, maybe my first sequence was this is like a sub n is this, and then b sub n conjugate was this, pretending like it came from two sequences multiplied together, we can see that the sum here was about 0.562, and then if we split that, and now we're looking at a sub n squared in magnitude, and we multiply that by b sub n squared in magnitude, then we see that we get a number about 1.652, which is definitely larger than 0.562. So there's another example of the Cauchy-Schwarz inequality, and in fact, it works with infinitely many entries. Okay, and this Cauchy-Schwarz in infinite dimensions is what's going to allow us to gain an inner product for the Fourier space. Because if we look at two entries of the Fourier space, I want to comment here, here's the remark. I had been using H for my arbitrary Fourier space entry before with some C's as my coefficients. I'm gonna move into just talking about my two functions in the Fourier space as f and g. These are going to be different f's and g's than they were in the last section. So this is just f and g being two elements of my Fourier space for an arbitrary theta 0, theta 1. And the coefficients of f are going to be a sub n. The coefficients of g will be b sub n. And we're going to see how to take an inner product of these. And over here, I say that I'm defining the inner product of f with g as an integral. Well, my Cauchy-Schwarz didn't say anything about integrals, so this is kind of strange that I introduced the inner product on the Fourier space as an integral of f against g with the conjugate of g, and then integrated over all of space and normalized over all of space. But let's just roll with that for now. Let's say, hey, we're going to let that be the inner product of f and g. And if I do, then I have this example, and I can compute, maybe I'll let f of theta be theta, and I'll let g of theta be cosine theta, and I'll fix my bounds of my domain as minus pi to pi. And I can compute their inner product, then all I do is I take f, I multiply by g, and I integrate over all of space. I go through a little bit of work to get there, and I get 0, and what do you know? There's inner product is equal to 0. We like to call that orthogonal. Now, I haven't really shown you why we should think about a definition like this as an inner product. But if I move down by one line, you'll see why. And that's right here with Parseval's theorem. So we recall Parseval's theorem from the previous section, but now I'm writing Parseval's theorem out a little bit more explicitly, and I'm claiming that the inner product of f with g is the infinite series over n, from minus infinity to infinity, of the coefficients of f times the conjugate coefficients of G. So recall, F can really be thought of as an infinite vector of a sub n's from minus infinity to infinity. G can be thought of as an infinite vector of b sub n from minus infinity to infinity. And it turns out that their inner product is the elements of F times the elements of G conjugate, and then summed over all of their indices. And that's why this looks like an inner product, because if I were to take the true dot product of these two functions right here, that looks exactly like the inner product of two infinitely long vectors. But Parseval's theorem tells me, if we jump back to the previous section, Parseval's theorem tells me that those two are the same. This was Parseval's theorem from the previous section. And that's why we can get away with defining the inner product of two functions on a Fourier space by an integral, even though that inner product is really looking like the inner product of vectors. And we like to jump back and forth between the two of them all the time. So let's look at an example here. So we have our example of the inner product of f and g, where f is theta and g is cosine theta. And we calculated by hand using the integral that their inner product was 0. If I jump down now and I decide to use my new version of inner product from Parseval's theorem, I take the coefficients for f of theta, and we calculated those in the last section. And now if I look at my coefficients of g of theta, it's not that hard to find out what these should be, because I know I can represent cosine in terms of the complex exponentials. And so the coefficients b will just be 1/2 and 0, 1/2 strictly when the power of e is positive 1 and negative 1. 0 everywhere else. If I then compute my inner product in the version of thinking about f and g as infinitely long vectors, and I compute a dot product of these infinitely long vectors, all I'm doing is I'm looking left to right, and I'm multiplying those two entries against one another and adding them all together. Well, everything's going to be a 0 because of this right-hand side vector. This is cosine. Everything's going to be a 0 until I run into 1/2, in which case I'll multiply by a 1, and that's my 1/2 right here. Similarly, I have a 1/2 times negative 1, and that's my minus 1/2 right here. And what I end up with is I times 0, or in other terms, 0. So we can see now that we can compute the inner product of f and g using the Fourier coefficients, or we can compute the inner product of f and g using an integral. Now, why should these inner products necessarily be finite? Well, let's look at the norm that would possibly be induced from an inner product. So this norm is arises out of finite dimensional vectors as the magnitude of a vector was equal to the vector inner product with itself to the 1/2 power. That was true for finite dimensional vectors, and we're going to define it to be true. Right, here's a definition. We're defining it to be true for infinite dimensional vectors. And in this case, if we have this, we're defining the norm on my function to just be its magnitude squared and then integrated over some region to the 1/2 power. And we can compute it. I've got an example here where we compute it for f of theta being theta over our favorite interval. We would get something like pi squared over 3. But because of the Parseval theorem, Parseval's theorem gives us a way of computing the inner product of two functions with regards to their Fourier coefficients. Well, if I put the same function into my inner product on both sides, all of a sudden I extract a norm. Here, if I look, I extract the norm of f, but I know that by Parseval, that norm has to be the sum of the Fourier coefficients squared. And that's the Plancherel identity. So we can either compute norms with integrals, or we can compute norms with Fourier coefficients. The next example I have is going to be used for one of your exercises, and I'm calling it twice the Basel problem. It turns out that if I use this Plancherel identity with the norm I calculated earlier, that f squared, when f is the identity function, so it's theta, then its norm on this space is pi squared over 3. If I plug those coefficients that we've been using this whole time into my Plancherel identity, I'm going to be summing all of the coefficients squared, and that exactly looks like the sum from n being going from minus infinity to infinity of 1 over n squared, and the Plancherel identity is telling me that that's pi squared over 3. So keep that in mind for one of your exercises. We're moving on to seeing why inner products necessarily exist over the Fourier space. If I jump up here to the Plancherel identity, you'll recall I defined the Fourier space. I defined my Fourier space as the space over which this was finite. So I defined it to be the functions with Fourier coefficients so that this sum was necessarily finite. Or in other words, the norm of my functions is necessarily finite. But the Cauchy-Schwarz inequality gives me that if the norms of my functions are finite, then their inner product must be less than or equal to the norms of the functions, and therefore my inner product is also always finite. So this is since norms on my Fourier space are always finite, Cauchy-Schwarz guarantees my inner products are as well. And that's the number one reason why we want to keep Cauchy-Schwarz in mind. It can guarantee you that inner products exist in the Fourier space. So let's look at this now. Because of this, we have this fancy notion of what's called an inner product space, which is any vector space, in this case the Fourier space, any vector space where the inner product can be guaranteed to be finite and satisfies the natural properties that the inner product should. And in fact, we have this very fancy word named after David Hilbert, the Hilbert space. Is actually a Fourier space is one of the kinds of a Hilbert space, and that just means that it's complete, but you don't have to worry too much about what complete means in this class. So here now I'm defining the Fourier/Hilbert space, which is the exact same Fourier space I defined earlier, but I'm changing my basis elements to this bold E sub n, where I just define bold E sub n later. And I'm retaining the property that my sums need to converge when I take the coefficients and magnitudes squared. But now I'm endowing the space with the inner product, and that's what gives me the Hilbert space. So once I add this inner product to the space, which I defined earlier as this integral, then I have an inner product on the space, and in fact I have a norm as well. There's a very interesting theorem that I'm going to bring up now. And it's not actually something that I want to talk too much about, but it's something that I should bring up. And that's that, in fact, the Fourier space is this interesting other space that might sometimes get tossed around, capital L2 of theta 0, theta 1. And the way we would normally define capital L2 of theta 0, theta 1 is the functions for which their magnitude squared over the bounds is finite. So you saw earlier that the Fourier space was the space defined where the coefficients squared summed were finite. The L2 space is the space where integrals of the magnitude squared are finite. But it turns out, thanks to Plancherel, that this is precisely the same as that Fourier series converging, or the Fourier coefficient squared converging. And so these spaces, L2 of theta 0, theta 1, are exactly the same space as the Fourier space we were worried about earlier. And moreover, we can represent any function. Suppose for some strange reason I knew that my function, when I squared it and took the integral, that this was a finite number. I can actually choose to represent that function as a Fourier space function by computing the inner product of the function against the Fourier basis and then reconstructing it with the Fourier series. Okay, we're going to skip the proof for that one. We're going to move on to this example. So if we want to see that maybe there's something that isn't in an L2 space, right? You might ask the question, how many things are in L2 and how many things aren't? Here's just a nice example. 1 over x to the 1/3 is in L2, but 1 over x to the 1/2 is not in L2. And we can just do that by computing the integrals of those functions. Now, the most important part of this theorem is this one right at the bottom. Okay, so I want to state that all continuous functions on finite closed intervals are representable on the associated open interval by their Fourier series. This is why the Fourier series, well, once again, I'm telling you, there are so many reasons why the Fourier series is used, but this is one of the great many reasons why it's used, is that you can represent any continuous function on a finite closed interval by the Fourier series. But they only converge on the associated open interval. Okay, moving on to the next section. I'm just going to talk very briefly, this is a very short section because I know this video is getting a little long. I'm going to talk briefly about what we call the Hilbert space little L2. Okay, so this is a little script L2, and it is a Hilbert space. So we're going to think a little bit about the Fourier space that we were just talking about, and we know that all of the functions in my Fourier space can either be defined using the coefficients along with the basis, but also now as an infinite vector, right? We want to jump back to this idea that we can live in infinite vector spaces. So we just take the coefficients from minus infinity to infinity, and we plug them into this vector that goes all the way from minus infinity to infinity. And we identify each of the basis elements as the vector which only has a 1 in the nth entry. We also know that we can take the inner product by taking the dot product of these two vectors, and we know that that inner product will converge. We do have to be careful though, because in representing the Fourier series that way, it is not C infinity, right? C infinity is the space of all infinitely long vectors with complex entries, and we do not have that. We have the restriction that the norms on each of these vectors actually converge, okay? And that's where I put this. An inner product must converge, which we know it does, thanks to the Cauchy-Schwarz inequality. So the Hilbert space, little L2, is really the natural extension of the complex dimension space CD as D goes to infinity. It's precisely the vector space. L2 is the vector space of infinite sequences such that the norm squared or the magnitude squared of their entries converges. And now you might be wondering, how is this different than the Fourier space? Because the Fourier space had that exact same requirement. And that's the point of this section, is that this is no different up to identification of basis elements from the Fourier space. Right, so the Fourier space is in particular, the Fourier space is just really this L2 of Z where I'm letting myself index my complex sequence from minus infinity to plus infinity. It's this L2Z, but we identify it with the basis E sub n, or the basis E to the in 2 pi divided by theta 1 minus theta 0 times theta, right? This is your most generic setting of the Fourier series. But when we want to actually plot it or reconstruct the function, we must identify the basis. But why this section is in the book is that we're thinking about, every time we use the Fourier space, we're just thinking about this little L2 of Z, which is really saying all I'm going to think about is infinitely long vectors which are doubly indexed by minus infinity all the way up to infinity. That's really the Fourier space, but that's also this little space L2, and these spaces are isometrically isomorphic is the word that we use to mean basically the same space up to identification of a basis. And of course these L2s have the exact same inner products that we saw from the Fourier space, but we can only define them with sums now, because all that these little L2s see are the sums themselves, and they also have the integrals, right, or the norms. But the integrals in the Fourier space were kind of being extracted once we've given them this very specific basis. But in L2, it's only the sums that exist. So here's how we want to think about L2, just as that Fourier space before, but now I'm never going to identify E sub n with the nice little complex exponentials. I'm only going to let E sub n be this infinitely long vector, and all of the A sub n's are going to be infinitely long vectors as well. So here's a nice example of showing why C infinity and L2 are not necessarily the same. If I take this element of C infinity 1 divided by the square root of n, that's a perfectly valid vector, and yet it doesn't have a perfectly valid norm, as in the case where I could calculate the norm in L2. So if I put this another way, if an element of C infinity has an L2 norm, which equals infinity, right? If this norm diverges, then that's not going to be in my L2, that should be an n, L2 of n space. Meanwhile, we can find a different element, maybe 1 over n squared, which is actually both in the C infinity case, because it's an infinitely long vector with complex entries, but it's also in L2 because the L2 norm here, if I calculate the L2 norm of the sequence, it's pi to the 4th over 90. And so that one converges, and I know I'm in L2. That should again be an N. So then the last important thing that I'm going to talk about is this final theorem that really says that all separable Hilbert spaces, which means all Hilbert spaces with a countable basis, countably infinite basis, are equivalent to each other in the sense of isometric isomorphism. And that's what I was kind of hinting at earlier. The way we would do this is to construct a map that only maps the basis elements from one space into the other space. And so long as that map is linear and invertible, then we gain an isometric isomorphism. This is basically one of your exercises. All right, that's all I have. Thank you very much. I'm sorry it was a bit of a longer day, but I hope this is really exciting stuff for you. All right, bye.